Here we start with a new sections, new chapters, and chapter 3. And this is about talking about the torsion. Torsion is about the deformation of a shaft and a shaft under torsions. Okay, so basically here we consider a circular shaft, and then the torsion basically applied is simply to twist the shaft. Okay, so basically say this is in equilibrium, so basically the torsion we using T to apply. So under this case, in these chapters we're going to study how to describe the deformations of this circular shaft, and then from there we want to study how to calculate the stress, and actually this is a shear stress. Okay, and then we're going to introduce a few terminologies like the angle of the twist. Okay, that is, and also we're going to study the applications static indeterminate properties, and then we will apply our knowledge to the practical design of the transmission shaft, and then finally about the stress concentrations. So why here we want to study the shaft, and basically here is one example here, and usually a circular shaft is used to transmit torque or torsions. Okay, and so either in the transmission shaft or in gears coupled shaft. Okay, so that is pretty common mechanical components. And then so here we try to be in these chapters be a standalone a topic just dedicated to this kind of the loading situations here. So our the object, the goal is to learn to how to determine the stress and the strength of the circular shaft, and the shaft can be solid, can be hollow. Okay, and then it is under equilibrium status of the torsions on the two sides here. So again, to reach such a template, which is going to as a template for our discussions later on, how to reach such a template that basically based upon the free body diagram again. Okay, so we take the free body diagrams. For example, here we will be interested in the middle portions of the shaft here. Then we simply take a free body diagram on this one, and then by figuring the given torque which can be produced from motors. Okay, then we can estimate the torque, and then that action reaction transmitted to here, and the whole as the elastic object, and then again transmitted torsion to the other end. So the whole middle portion basically by itself form a static equilibrium conditions here. So everything is static equilibrium. That means summation of the torque, this one plus this one should be equal to 0. However, internally this shaft, any material points in the shaft is under torsion. Okay. So before we go to the big pictures, and here, so before we go to the details, here is the big pictures here. The first thing is everyone must at this point must know that the distributions of the stress inside in the cross section, okay, distribution of the stress in the cross section is not uniform. Please keep this in mind. This is the very different from what we have learned from previous chapters. From the chapter 2, we learned this. Our model is this is the force, and this is the cross sections, and then we know the stress average equal to P divided by A, and then under that situation, the stress is this number is the same everywhere in any point on the cross section. Okay, so let me take the free body diagram here. So in the free body diagram, then our expression of the stress is like this. That is uniform. However, for the torsions here, I can tell you the stress, and I will explain why, but the stress is not uniform. However, it is in linear distributions, and that linear distribution is proportional to the distance from the center of the shaft, and the maximum is on the parameters minimum as at the center here, and the distribution of the magnitude of the stress, and that is in linear distributions, and that is the very big difference. That is a very big difference than from what you have learned. So keep this in mind before we move on.